Hello, hello, guys. Good morning. Is everything all right? Can you hear me properly? Is everything all right? Today, in this session, we'll be discussing angular momentum. But the problem is, the pen tab is not working. Just a moment. Good morning, Karthik. Okay, so everything is all right, I hope. Let's move on. Good morning, good morning. So this is the first part of our angular momentum topic. So angular momentum you already know. Let us start the discussion with the classical definition which you have. So the topic name broadly angular momentum, very simple topic, okay? Angular momentum. Let us talk about orbital angular momentum. Orbital angular momentum. So in classical mechanics, if you have a particle, how do you represent its angular momentum? So in classical mechanics, the angular momentum L, angular momentum L of a particle. Angular momentum L of particle is defined as, how do you define it? If you remember, we defined it by this relation, L is equals to R cross P. Okay, R is the position vector, P is the momentum. So if you expand this, how do you get I cap, J cap, K cap, then component of R, X, Y, Z. Thereafter we write the component of P, Px, Py and Pz, and this can be written as, you see, Ypz minus Zpy, Ypz minus Zpy I cap plus J, you see, Xpz minus Zpx, but we have taken my plus, so you have to add a minus, so this becomes Zpx minus Xpz. J cap plus Xpz, sorry, Xpy minus Ypx K cap. So this is the component along the x direction. If I talk about it, this is nothing but, we can write it in this way, this is equals to Lx I cap plus Ly J cap plus Lz K cap. So this is the classical definition, right? Now if you want to switch it to quantum mechanical expression, what you do, you just need to replace this position and momentum thing into their corresponding quantum mechanical operator. Okay, so if you replace the position and momentum by their corresponding operator, by replacing the position and momentum coordinates by the equivalent quantum mechanical operator, what we can have, let's say I am writing in two set of coordinates. So we require Cartesian coordinate and we also require spherical polar coordinates. So we are writing the two coordinates side by side. Firstly, we will write in terms of the Cartesian coordinates, then we will write in terms of the spherical polar coordinate. Here we will be writing Cartesian coordinate, Cartesian coordinates. Here we will be writing spherical polar coordinates. Okay. So first of all, we have Lx equals to, as you can see, Lx is equals to ypz minus zpy. So we have to replace with their corresponding operator, quantum mechanical operator. So this is Ls cap ypz minus zpy. So it will become capital, okay, ypz minus zpy. So we have to add caps to make them quantum mechanical operator. Now you know y is y, pz you know minus I h cut del z. So minus I h cut and y cap is y cap. This is del del z minus z cap del del y. Okay, this is actually capital Z. Okay, you just imagine it to be capital Z. Capital Z. Similarly, we can write Ly. Ly, how will write Z px minus x pz. So this is minus I h cut z cap del del x minus x cap del del z. Okay. Next, Lz xpy minus y px minus I h cut x del del y minus y cap del del x. So this is in the Cartesian coordinate. So they have the corresponding expressions in the spherical polar coordinate as well. In the spherical polar coordinate, we can write it, the equivalent expression is minus I h cut minus sin phi del del theta minus cot theta cos phi del del phi minus I h cut cos phi del del theta minus cot theta sin phi del del phi, and finally this one minus I h cut del del phi. So you don't need to remember this in spherical polar coordinates. You only need to remember the last one, Lz. Lz is important, minus IH car del phi. This one you need to remember in spherical polar coordinate. While solving problem, this will come repeatedly, Lz part. Okay. Now you see, we have L is equals to Lx I cap plus Ly j cap plus Lz k cap. So what will be the value of L square? L square will be Lx square plus Ly square plus Lz square, right? Now if I talk about a quantum mechanical operator L square, it has a very special form. L square is equals to minus h cut square 1 by sin theta del theta sin theta del theta plus 1 by sin square theta del square del phi square. So look, in the discussion of angular momentum, we need to mainly focus on two things. One is L square, another one is Lz. These two things are very important. Okay, L square and Lz. So L square, the quantum mechanical operator expression is given by this minus h cut square 1 by sin theta del theta sin theta del theta plus 1 by sin square theta del square phi del phi square. Now we have different components of the angular momentum, Lx, Ly, Lz. So we will also have some commutation relation between them. So let us write some commutation relation between them. Commutation relations. Just a moment. So let's talk about the first commutation relation, Lx, Ly. What is the commutation between Lx, Ly? It is equals to I h cut Lz. So we will have a cyclic relation between Lx, Ly and Lz. Okay. So if you take the commutation between Lx and Ly, you get I h cut Lz. Ly and Lz, if you take the commutation relation, you will get I h cut Lx. Okay, Lx Ly. Then okay, let's say Ly Lz I h cut Lx Lz Lx I h cut Ly. Now if you just make it opposite, the Ly Lx, so obviously it is going in the opposite direction, so it will be minus I h cut Lz. Similarly for this one, Lz Ly, this will be minus IH cut LX, and here it is LX. LZ if you take, it will become minus IH cut LY, as simple as that. So what does it mean? What is the physical significance of it? The commutation between two components of the angular momentum is non-zero. It means the two components of the angular momentum cannot be measured simultaneously. That is what the meaning is now. That is, the components of the orbital angular momentum. Look, for the time being, we have kept our discussion limited to orbital angular momentum. It has two parts. One is the orbital angular momentum part, and later we will be discussing spin angular momentum part. Okay. So for the time being, we are focusing on the orbital angular momentum part only. That is the components of the orbital angular momentum cannot be measured simultaneously. Accurately. Heisenberg uncertainty principle, you have seen the general Heisenberg uncertainty principle. From that we conclude that if the commutation is not zero, we cannot measure them simultaneously. Sorry guys. Okay, what I was talking about, if the commutation relation is non-zero, we cannot measure those two things simultaneously accurately. Now if I take the commutation between L square and the components like L square and Lx, it will give you 0. L square Ly, this will also give you 0. L square and Lz, this also gives you. What does it mean? Although we cannot measure the components simultaneously, the square of the angular momentum, and any component of the angular momentum can be measured simultaneously accurately. Okay. Is there any confusion till now? Everything all right? Let's move on to the energy eigenvalue of L square and Lz. Sorry, eigenvalue and eigenfunctions of L square and Lz. So as I told you also before also, we are mainly focused on L square and Lz. So we need to know eigenvalues and eigenfunctions of L square and Lz. Look, we have got this commutation bracket L square Lx or Lx square, particularly Lz. This is 0, so they commute. So you can say L square and Lz can be measured simultaneously. So can be measured simultaneously. This is one thing. Now, when they can be measured simultaneously accurately, they will have shared eigenfunction. Okay, and both have simultaneous eigenfunctions. Simultaneous eigenfunctions or eigenkate. Eigenfunctions or eigenkates. It means whatever be the eigenfunction will be of L square, Lz will have the same set of eigenfunctions. So let's denote that eigenfunction by Lm. Denoting the simultaneous eigenkates by, look, L m. There is a fundamental difference between this capital L and small l. Capital L, orbital angular momentum. This small l, these are quantum numbers. Orbital quantum number is magnetic quantum number. Okay, so basic difference you need to understand. So denoting the simultaneous eigenkates by Lm, where L is the orbital angular quantum number. Orbital quantum number, and m is the orbital magnetic quantum number. So if you take the simultaneous eigenkates to be Lm, the eigenvalue equation for L square and Lz can be written as. So this is very important. How do you write the eigenvalue equations for them? So you know how to write eigenvalue equation. L square and Lz, they are having simultaneous eigenfunctions, means this L, and let's say denote by ml. Okay, here also you just add it ml. So they will be having same set of eigenfunction, but the eigenvalues will be different. The eigenvalue of L square is L into L plus 1 h cut square. Eigenvalue equation means this LML will remain same. Lz, the eigenvalue of Lz is mh cut. So ml h cut, L ml, and you know the limit. Here one thing you should write it as a note. The value of ml, you know, it has a value from, it can take values from minus L to plus L, right? So this is these are the two relations which you need to know. But actually you know, it is not difficult. We have already studied about them. Any question till now? Let's move on to a problem. If Lx, Ly, Lz are the components of angular momentum operator in 3 dimension, the commutator Lx, Ly, Lz may be simplified to. Do it quickly. Is it done? Hari, Karthik, Murli, could you solve this problem? Simple problem. We have to find out the commutation relation of Lx, Ly, Lz. So what have you done? Look, you can consider these to be two units. Lx is one unit, Ly, Lz is other unit, right? So it can be written as Lx, then Lx, Ly, Lz, later Lx, Ly, Lz. So the second term is vanished. Later Ly and Lz. So Lx. We can take it as common. Now let's evaluate the commutation between this. Okay, or simply we can write it in this way: Lx, Ly, Lx, Lz plus Lx, Lx, Ly, Lz. Now Lx, Lz, you can draw this cyclic thing. It will help you to decide without any mistake. Lx, Lz. So we are going in the opposite direction, anti-clockwise. So it will be minus. So Lx, Ly. This is minus I h cut Ly plus. This is Lx, Ly. Going in the clockwise direction, this will be plus I h cut Lz, Lz. So minus I h cut, okay, I h cut, what can be taken common? I h cut Lx you can take common. So if I take I h cut Lx common, so from the second term we are getting Lz square, and from this we are getting Ly square. So option A is matching. Yes, Harry, Murli. Now, as I told you, this L and M, LML, this is the eigenfunction, shared eigenfunctions we have told you. So it will have alternate form. If I write it in the spherical polar coordinate using the spherical harmonics, what you get? Look, since we have seen that L square and Lz, they are dependent on theta, right? L square you can see depending on theta and phi. Lz depends on phi. So let us talk about that. Since L square and Lz depend on theta and phi, so their eigenfunctions their eigenfunctions are the function of theta and phi. That is, look, this is L square, this is Lz. So they have both simultaneous eigenfunctions. So let us now denote the eigenfunction. Instead of LML, we are denoting it by YLM theta phi. This is some function which is an eigenfunction of both L square and Lz. So YLM theta phi is the eigenfunction of both L square and Lz. So obviously here L is there, so L into L plus 1 h cut square y, yes, right, ml. So this is, you can say, alternate form in the spherical polar coordinate. Why? What is this y L ml? This y L ml of theta phi is said to be the spherical harmonics. It's said to be spherical harmonics. And it is defined as the following expression, defined as by the following expression. Okay, y L ml of theta phi. You don't need to remember this. Okay, this is a complicated expression. Okay, you for the sake of completeness, we are just providing you this value, but you don't need to remember it. So don't take stress. 12 plus 1 by 4 pi L minus modulus of ml factorial L plus modulus of ml factorial, then outside of it PL to the power ml cos theta e to the power I ml phi. Okay, where this epsilon is equals to minus 1 to the power ml for ml greater than 0, and this is 1 for ml less equals to 0. But this is just for your information, you can ignore it. Okay, just remember that these two things hold. You know that quantum numbers, if I talk about L, that is orbital quantum number. If I talk about ml, that is orbital magnetic quantum number. Another one is n. N is the principal quantum number. So sometimes we write the wave function psi in spherical polar coordinate as a function of n, L, ml. Okay, so the first letter represents the principal quantum number, second letter represents the orbital quantum number, third letter represents the orbital magnetic quantum number. Okay, so if I am giving you psi, let's say 2, 1, minus 1, what does it mean? It means it has a value of n is equals to 2, L is equals to 1, m is equals to minus 1. So you know, for L square and Lz, the eigenfunction depends only on L and ml. Okay, so L and ml, so we need to consider only these two things. In a similar fashion, if you have psi 210, It means n is equals to 2, L is equals to 1, ML is equals to 0. Okay. So, I am giving you a problem involving this. So, look at this problem. Let psi n L M L denote the eigenfunctions of a Hamiltonian for a spherically symmetric potential V of R. The wave function is an eigenfunction only for when it is called eigenfunction. If you can find out, let's say A is an operator, right? If you find out a relation like this, some multiplicative factor into psi, if you can express it in this way, then we will be calling it an eigenvalue equation, and psi will be called as an eigenfunction, right? Eigenvalue equation. If we can present it in this way, then it can be said that this is an eigenvalue equation and psi is the eigenfunction, and whatever constant you will get here, that will be your eigenvalue. Now, what is it asking? The wave function psi is an eigenfunction only of. Okay. So, A, you have to check it with H. So, H psi is equal to some constant of psi. If you get, then we can say that this psi is an eigenfunction of H. We will later replace A by L square. So, L square into psi, if you can find out something into psi, then we can say that L square, this psi is the eigenfunction of L square. Similarly, for Lz, you will put Lz psi. If you get something into psi, we can say that psi is the eigenfunction of Lz. Okay. So, you have to check for 3 of them, and you have to decide which one is the correct option. Give it a try. Option C, found so quickly. Did you check for every option? Look, what do we know? We know this relation that L square, let's say if you operate on psi n L M L, what it will give you? It only depends on this L factor, L into L plus 1 h cut square psi n L M. Okay, and Lz while operates on psi n L M L, this gives you M L h cut psi n L M L. Is that clear? Now let's check for H. We are checking for H. So what we have to find out? H psi is equals to E psi. This is very well known. H psi is equals to E psi. We know Schrodinger equation. Let's check whether it is valid or not. H psi. So if you apply H on everything, so 1 by 4 H will be applied on psi 210 plus square root of 5 psi2 1 minus 1 plus psi2 1 1. Now we know a relationship that h psi is equals to E psi, right? The eigenvalue you get to be energy. Now energy depend on n value. Okay, now here 2 is there, so principal quantum number n decides the energy value, right? So what will be the value of this thing? This is equals to, look here, everywhere n is equals to 2 is there, so energy value will also be same. So we are writing that to be En. Okay, En by 4, h psi is equals to E psi, so E is equals to En, n equals to 2, h psi is equals to E psi plus E we have taken already, so just psi2 1 minus 1 plus root over 10 psi2 1. So as you can see, this is En by 4, this is En of psi. So we can say that h is the eigenvalue, sorry, psi is the eigenvalue of h, is an eigenfunction, sorry, not eigenvalue, eigenfunction of h. So we have checked h. Let's go for L square. Let's check L square, and you know how L square behaves. L square will produce L into L plus 1 h cut square. So L square operating on psi 1 by 4 L square psi2 1 0 root 5 L square psi2 1 minus 1 square root of 10 L square psi2 1 1. So it will only target L square, so L into L plus 1 h cut square. So here it is 1, here it is 1, here it is 1. So 1 into 1 plus 1 h cut square means 2 h cut square. So 2 h cut square by 4, and this will remain as it is, psi2 1 0 psi2 1 minus 1 psi2 1 1, and this is nothing but 2 h cut square times psi. So here also we can say that psi is an eigenfunction of L square, right? Let us now finally check for Lz. Will Lz be also falling into the same category? Let's check. Look, this will be 1 by 4. Lz operates on ML h cut. So you see 0 is here, so it will become 0 plus square root of 5 Lz operating on minus 1, so minus ML minus 1 h cut psi2 1 minus 1 square root of 10, here it is plus 1 h cut psi2 1 1. Okay, so as you can see, we cannot express it as some constant times psi. It is not expressible. This is 0, so we will not get back h, we will not get back psi. Hence we can conclude that psi is not an eigenfunctions of Lz. So look at the options now. The wave function is an eigenfunction only of, as you can see, h and L square. So option C. Is it clear? Harry, Murli, Karthik? Let's move on. The wave function of a state of the hydrogen atom is given by this. Hydrogen atom will cover, but it will not require the knowledge of hydrogen atom here, where psi NLML is the normalized eigenfunction of the state with quantum number NLM in the usual notation. The expectation value of Lz in the state psi. Okay, you have to find out Lz in the state psi. Will you give it a try? Getting the answer, guys? What is the expectation value of Lz? So we can just simply use the formula of expectation value. You have to find out expectation value of Lz in the state psi. So psi Lz psi divided by psi, as simple as that. Okay. So you can write this expression, let's say this expression of psi, you can write it as a like C1 psi 2 0 0 plus 2 is C2, let's say psi 2 1 1, C3 psi 2 1 0, C4 psi 2 1 minus 1. Okay. So if I can write it, can we not write it in this way, that it is sum over, let's say L modulus of CL square ML H cut divided by sum over L CL square. Can I write it? Commutating operators having common set of eigenfunctions, then how it cannot be the same eigenfunction for L square and Lz in the last problem? Very good question. Commutating operators, they can have simultaneous eigenfunctions. It doesn't mean that all of the eigenfunctions will be simultaneous. Okay. It is like two friends, they can have common friends. So it doesn't mean that they individually cannot have friends. You can think in that way. Look, what will be the first term? CL square. So C1 L equals to 1, C1 square. So 1 square is 1. ML H cut, ML is 0 here. So 0 H cut. Next term C2 square. So that is 2 square. 2 square. Let's write it in this way. 1 square. 2 square. And ML value is 1. Okay. 2 square. What is the ML value? ML is 1. 1 H cut. Next 3 square. ML value 0 H cut. Root 2 square. ML value minus 1 H cut. Is it clear or not? Divided by 1 square plus 2 square plus 3 square plus root 2 whole square. Murli, is it getting clear? And this is equal to 4 H cut minus 2 H cut divided by 1 plus 4 5 plus 9 14 plus 2 16. 2 H cut by 16 it means H cut by 8. Very simple. If you go in a systematic way, you can easily do it. And if you are wondering why this expression is coming, it is simple. When you calculate LZ psi, you get ML H cut psi, right? Now you have to take bra psi LZ psi. It means ML H cut bra psi ket psi, and this is ML H cut bra psi ket psi, the scalar product, that is the coefficient square. That is why we have written this. Now I think it is clear. This is ket psi. When you write the bra psi and you take scalar product, you get the coefficient square only, okay, because of the orthonormalization condition. Murli, is it clear now? Harry, Karthik, what about you guys? Okay, let's move on. Do this one. So similar problem came in many years. If you can see, June 2013, similar problem. Psi NLM denotes the eigenfunction of the Hamiltonian with a potential V of B equals to V of R. Then the expectation value of Lx square plus Ly square in the state psi is. Do it. Lx square plus Ly square. So we only know about L square and Lz. So if I am talking, if you are asking, you are being asked about Lx square plus Ly square, So we'll just convert it in terms of L square and Lz. So you know L square is equals to Lx square plus Ly square plus Lz square. So although they are asking you about Lx square plus Ly square, you are seeing them as L square minus Lz square. Look, L square you know, Lz you know, Lz square will be, look, for Lz if it is ml h cut, Lz square will be ml square h cut square, as simple as that. Now I think I have given you a good hint. You should now be able to solve this problem efficiently. Look, the orthonormalization condition will look like this. I am writing the orthonormalization condition here. Let's say n L prime m prime. If we consider that n is same, n L m. So this is equals to delta L prime delta m prime. Okay, this is what the orthonormality condition looks like. Can you do this problem? Look, Lx square plus Ly square, but we know only in terms of L square and Lz. So first of all, we are writing Lx square plus Ly square as L square minus Lz square. So the expectation value of Lx square plus Ly square is equals to the expectation value of L square minus Lz square. So this can be written as expectation value of L square minus expectation value of Lz square. Okay. Now look, the wave function is given to be normalized. How to check whether the given wave function is normalized or not? So you see, given psi, we are writing in terms of the ket notation, bracket notation, 1 upon 5, okay, 3 ket psi 2 1 1 plus ket psi 2 1 0 minus square root of 15 ket psi 2 1 minus 1. Okay, so corresponding expression for bra will become, look, quantum mechanics, you need to practice a lot of problems, then only it will come under your control, otherwise it will be very difficult for you. 3 is a real number, so 3 psi 2 1 1 bra psi 2 1 1 plus bra psi 2 1 0. Look, these numbers are real numbers, so it doesn't matter whether you take a star, they remain same, right? So what is psi psi? 1 by 5, 1 by 5, 1 by 25, 3 into 3 9, 1 into 1 plus 50. So as you can see, this is 25 by 25, that is 1. So when that is why we can say hence psi is normalized. Okay. So when we, if psi is normalized, when we calculate the expectation value, we don't need to divide by psi psi, because psi psi is already 1, right? So you see, let us try to find out the expectation value of L square. So we need to find out the expectation value of L square and Lz square, then we'll just subtract. So expectation value of L square is psi L square psi divided by psi psi. psi is 1 because it is normalized. Psi L square psi. Can we not find out psi L square psi? So this is bra psi. Bra psi you put 1 by 5, 3 psi 2 1 1, psi 2 1 0, psi 2 1 minus 1. Okay. Then L square ket psi 1 by 5, 3 psi 2 1 1, psi 2 1 0, square root of 15 psi 2 1 minus 1. Okay. So as you can see, this is 1 upon 25, 5 into 5. Look, if it is bra, then 3 can be written here, okay, on the opposite side. Psi 2 1 1, 3, psi 2 1 0, psi 2 1 minus 1, root over 15. Now L square operating on this first term, what it will give you? L square means L into L plus 1 h cut square. So here it is L equals to 1. So 1 into 1 plus 1, 2 h cut square. So 3 into 2 h cut square psi 2 1 1. Next, here also again it is 1. So 1 into 1 plus 1, 2 h cut square psi 2 1 0. Let me know when at any point if you are not able to understand. Here also 2. So minus square root of 15 was there into 2 h cut square psi 2 1 minus 1. Now using the orthonormality condition, orthonormality condition as I have already told you. N L prime M prime N L M delta L prime delta M M prime. Sir, can't we do the expectation value calculation in the shortest method as we did in the previous question? Of course we can do. Because it was yes, actually the same thing. CL mod CL square ML h cut. Now it will not be ML if you are talking about L square, so it will be L into L plus 1 h cut square. Okay. Yes, you can obviously do. We are just doing that only. We are just doing that only. Psi is 1, so we don't need to do that. So it is like we are doing this only. If I am writing it CL mod CL square L into L plus 1 h cut square. This is what we are doing. Okay. So you can just like you can break it and you can do it, but you can simply use this formula. Same thing. Once you understand, you can play around. So 1 upon 25. Even if you go with this, you will get the same result. No issue. Okay. So psi was the coefficients square. So 3 square L into L plus 1 2 h cut square plus 1 square again 2 h cut square plus square root of 15 square minus square root of 15 square, and how much? Again 2h cut square. So what are you getting? 9 into 2. 2h cut square we can take a common. 2h cut square by 25. 9 plus 1 plus 15. 25 by 25. 2. 2h cut square. So L square we got 2h cut square. Now next what we have to find out? LZ square. So if you are comfortable with that formula, LZ square will be again psi LZ square psi divided by psi. Psi is 1, so it is psi LZ square psi. So if you are comfortable with this formula only, I am just giving you. So what will be this? Again, modulus of CL square, LZ is ML h cut, LZ square, so ML square h cut square. Okay, this is what it is. So 3 by 25, okay, 3 by 5 was there. So 1 by 25 we are taking outside, it is common. 3 square, ML square h cut square. What is the ML value for first one? Psi 2 1 1. So 1 square h cut square. Next 1 square 0 square h cut square. Next plus minus of root 15 square minus 1 square, so minus 1 square h cut square. So how much we are getting? 9 h cut square by 25 h cut 9, and from here it is 15. 24 by 25 h cut square, and hence we are writing that Lx square plus Ly square, the expectation value of Lx square and Ly square, it is the expectation value of L square minus Lz square. L square we have got 2 h cut square, Lz square 24 by 25 h cut square. So this is 50 minus 24 by 25 h cut square, so it's 26 by 25 h cut square, and that's matching with option D. How simple it is. Harry, Murli, where are you guys? Able to understand? Look, here we would like to mention one thing. So if you have some space, you can add this thing, little bit of theory. You already know L square is equals to Lx square plus Ly square plus Lz square. Now you see, expectation value of Lx square is equals to Ly square, we can write it, okay. And you see, this is what Lx square, the expectation value of Lx square and Ly square same. So it is 2 times Lx square we can write. So half time it is L square minus Lz square. Can I write it? Another thing, expectation value of Lx and expectation value of Ly, they are same, that is 0. Lz and L square they will give different result, but Lx and Ly their expectation value are 0. And expectation value of Lx square and Ly square will be decided from this L square minus Lz square. You can see it is very easy to understand from this equation. Let's take the expectation value on both sides. L square expectation, Lx square, Ly square, Lz square. So they are equal. So 2 times expectation value of Lx square plus Lz square. So Lx square expectation value is equals to half time L square minus Lz square. Okay. Or if it is inconvenient for you, you can just add another line here to make it simplified for you. L square, Lx square, Ly square, Lz square. Okay. Lx square, which is equal to Ly square, equals to half times this. I hope this is clear. Let us now one last problem today. This one. Consider an eigenstate of L square and Lz operator denoted by Lm. Let A is equals to n cap dot L denote an operator where n cap is a unit vector parameterized in terms of 2 angles as nx, ny, nz. The width delta A in Lm state has the following property. A is equals to n cap dot L. So you have to find out delta A. Delta A in a standard deviation. So you know delta A is equals to square root of A square average minus A average square, or expectation value of A square minus expectation value of A whole square. So to get to know about these things, we need to know about A first. Read the question. If I give the solution, then you will not learn. You have to read and try. Then you can do this problem. Acha, another thing I remember. What is the expectation value of L square? That you know, na? Look, h cut square we are taking common. Expectation value of L square is L into L plus 1 h cut square, okay, minus Lz ml h cut, so Lz square, so ml square h cut square. So that is why we write it in this way. Okay. Okay, I want you to try it by yourself first, then I will give you the solution. I am just giving you a hint. You need to find out this, there is no confusion in it. Now about this A is equals to n cap dot L. Let me just give you a brief hint about this, then we will discuss this on the next day. A is equals to n cap dot L. This is given to you. Okay. So the n cap is the unit vector given by, you can see, sin theta cos phi, sin theta sin phi, and cos theta. Okay, nx, ny, nz. So n cap dot L we can write Lx into x by r plus Ly y by r Lz z by r. Clear? N cap is the unit vector. You can see here. It is like r sin theta cos phi, r sin theta sin phi, and r cos theta. So that is why we have divided by r, and you get this one. Getting it? So x is in a spherical polar coordinate, it is written as r sin theta cos phi, Ly r sin theta sin phi, and Lz z is equals to r cos theta. We know this. So this is Lx sin theta cos phi, Ly sin theta sin phi, Lz cos theta. Okay. We could have directly written it because it is already given that n cap is a unit vector and it has the component like this. So it is like n cap dot L. It is like nx Lx plus ny Ly plus nz Lz. Right. You can also write it here. It is like nx Lx or Lx nx, whatever you write. Ly ny Lz nz. So we have just tried to explain. You can directly write this fourth line from the first line, but we have just shown you how it is coming. So once you know A, we can find out delta A after evaluating A square average and A average square. Now A square average, if you want to calculate A average, so A value we know, so we have to take look what we have, Lx sin theta cos phi, Ly sin theta sin phi, and Lz cos theta. When you are taking the expectation value of, means taking expectation value of Lx, Ly and Lz. Okay. Then you can easily calculate. We have already told you what are the expectation value of Lx, Ly and Lz. Expectation value of Lz is what? Okay. Here you can include. You already know what is the expectation value of Lz. It is MLH karna. So in this way, by putting the values of this thing, you can find out A. Similarly, you can find out A square. A square. A square. What will be, if A is this, what will be A square? You know it. You can find out. A square will be Lx square sin square theta cos square phi, Ly square sin square theta sin square phi, Lz square cos square theta. Then you will take the expectation value of Lx, Lz square. Okay. Then you have to find out delta A and you have to find out the minimum and maximum value actually. Will you be able to do it? I have just provided almost 60% of the solution I have already given you. So you have to think about it as a whole and you will try it at home. Will you be able to do it? If you have any question regarding this question, you can ask. If not, then we can stop the session here. Okay. Okay, so let's end the session here. You will try this at home and we can start discussing this question in the next class. Bye bye. Take care. Have a great day.